All right, on that note, let's get underway. It is indeed a pleasure to welcome Joel Myers back to Toronto. Joel's academic history starts with undergrad work at Wisconsin, and then his PhD was with Steve Weinberg. And the dissertation title I gather was Inflation from Theory to Observation, a topic that remains highly relevant to this day, both to the field generally and to Joel's work in particular. He was with us at CITA as a postdoc fellow and a senior research associate from 2012 to 2018, after which he served his current position as an assistant professor at Southern Methodist University. Joel's interests continue to include cognitive inflation, but also light relics, all kinds of different ways in which we can use CMB observations to learn about the universe. He's a member of Science Observatory, CITA, CMBS4, where he's a science co-chair, and he'll be talking to us today about all of these upcoming surveys and the opportunities and challenges that they present. So with that, I'll let Joel take it away.
Excellent. All right. Thanks very much, Dong-Woo, and thanks for the invitation to be here. It's always great to be back in Toronto. Very happy to be here, especially in the summer when the weather is nice. All right, so as Dong-Woo said, I'm going to be talking to you today about all of the exciting opportunities that are offered by upcoming CMB observations. And I'll also talk to you a little bit about some of the challenges that we have to overcome in order to make the most of those upcoming observations. So, as cosmologists, our goal is to describe 13.8 billion years of cosmic history. The CMB plays a particularly important role in that because it gives us a snapshot of the universe as it was when the universe was about 380,000 years old at the time of recombination, when the universe transitioned from being filled with a hot, dense plasma that was opaque to radiation to being filled with a neutral gas that's transparent to radiation. And so when the universe became transparent, all the photons that had been rattling around with this plasma prior to recombination were then free to propagate. They've been freely propagating to us ever since, and we observe that background of radiation as the CMB. That provides a snapshot, again, at about 380,000 years after the onset of the hot Big Bang evolution. And so we get information about the content of the universe around that time and sort of the integrated expansion that's taken place since. Now, when I was here last, about a year ago, a little over a year ago, I made a big point that there's a huge amount of extra information that you can learn about the much earlier periods that imprint themselves onto the surface of last scattering. And how that's really exciting because it gives us sensitivity to very high energy physics, very weakly coupled potential new physics beyond the standard model that might point the way towards some of the big open questions in all of physics, like the nature of dark matter, the fundamental constituents of the universe, and the interactions among those constituents. I won't bore you with the same talk today, so I'm going to leave that mostly aside and instead talk about a different regime in which the CMB can give us a great deal of insight beyond just this surface of last scattering. In particular, I'm going to talk to you today primarily about the ways in which all of the structure that intervenes between us and the surface of last scattering is imprinted on our observations of the cosmic microwave background. All right, so a quick outline of the talk is that I'll give you a very brief overview of cosmic microwave background science, what it is, what information does it encode, and how can we use those observations to learn about the universe. I'll then move on to talk about gravitational lensing of the cosmic microwave background, how photons are deflected on their path to us by the structure that intervenes between us and the surface of last scattering. I'll talk a little bit about why we care, using one specific example, that of measuring the mass of cosmic neutrinos. And then I'll use that as motivation to say that we want to extract the best possible lensing measurement we can and talk about ways that we have proposed to do that. And then I'll talk about ways in which we want to remove the effects of lensing to try to get a more pristine view of the surface of last scattering, unimpacted by things like lensing and other related effects. And I will then talk about some machine learning approaches to extracting information from these so-called secondary anisotropes, these imprints of the structure that lie between us and the surface of last scattering, and then I'll wrap up. I should say I probably have more information than I'll get through, so if there are things you want to hear more about, please do interrupt with questions anywhere throughout. I won't be offended if I don't get all through all these topics. All right, so let's start with a quick review of CMB science. So the cosmic microwave background, as I briefly mentioned, was formed when the universe transitioned from being filled with a hot, dense plasma to a transparent gas. And the radiation has been propagating to us ever since. Because the photons were in thermal equilibrium with that hot, dense plasma in the early universe, they've maintained that thermal distribution, which forms this perfect Planck black body, which we've measured at very high precision and agrees very well with theoretical expectations of perfect thermal distribution. Just this spectrum tells us a huge amount about the universe. It very strongly indicates that the universe obeys this hot Big Bang evolution, that it was a very, very different place in the past than it is today, that it's undergoing this expansion and has been doing so for about 13.8 billion years. There's much more information that we can gather, not just by considering the average properties, like this thermal spectrum, but by considering the way that this deviates, that our observations of the cosmic microwave background deviate from being perfectly uniform throughout the sky. And the physics of this carries a lot of interesting information about the history, contents, and evolution of the universe that can be understood by thinking about the way that sound waves propagated through the primordial plasma. Now, we know that the universe in this time around the surface of last scattering, around the epoch of recombination, was dominated by 4 different fluids: dark matter shown in black, gas, which is the baryonic matter, atoms and photons, and electrons and protons, the photons, the cosmic microwave background itself, and then neutrinos. Now, these things all interact via gravity. The photons and the gas interact via Coulomb scattering, and the dark matter interacts only gravitationally with everything else. And these 4 constituents evolve due to a spectrum of initial perturbations, and they propagate, those perturbations propagate through each of these fluids in a way that's determined by those interactions among the species. And so what you can see, what you're seeing is an animation of a single perturbation to all of these fluids, a so-called adiabatic perturbation where all the fluids are perturbed in the same way. And you can see that each of the species behaves a little bit differently. So for example, for dark matter, the perturbation, initial perturbation, just spreads kind of weakly outward. For the gas and the photons, they form a coupled fluid for much of the evolution at early times, and then they separate at late times. I'll come back to that statement in just a moment. And then neutrinos, which propagate outward at the speed of light, or in this diagram, the speed of light over square root of square root of 3. And all of the physics of those sound waves get encoded in our observations of the CMB. But there's a particular time I want to reference here, which is this time that's noted by recombination. And in this animation, it occurs when the blue line and the red line separate from one another. And that is when the photon baryon fluid changes from being tightly coupled, when these lines stick together, to when the photons begin their free propagation, their free streaming. And that occurs around the time of that 380,000 years, which you can see, which you can verify up here, or a redshift of about 1100. And it's that instant at which we get a view of the early universe by making observations of the cosmic microwave background. And as you can imagine, and then this later physics is also very interesting. It won't be the content of what I talk about today, but the fact that this bump is left here in the distribution of both the gas and the dark matter is what results in the baryonic acoustic oscillation feature that appears in the distribution of galaxies throughout the universe. So a lot of interesting physics in here. The only thing I really want you to take away right now is that if you change things like the relative abundances of these fluids, if you change the way that these things interact, if you change anything about this picture, you'll change what you get left with at this instant when the photons separate from the baryons, and that will be imprinted in our distribution of the photons that we observe in the cosmic microwave background. So all of this is linear physics. It's all linear physics that's understood in terms of just the electromagnetic interactions between the gas and the photons, and gravitation. And so all of this physics is clearly understood linear. If you change the ingredients, you change what we get. But the fact that we can calculate it all for any given cosmology is really important for what I'll say about looking for distortions from this standard picture. Now, of course, what we have in the real universe is not just a single perturbation isolated somewhere in space, but we have a very wide range of perturbations spread across the whole universe. And so what we observe is not a single characteristic peak like this, but you can imagine that this physics is at play, but with initial conditions that give us variations in the density from place to place all across the universe. So this is a very nice animation put together by Adam Hinks from U of T that demonstrates how you can start with this very widely varying spectrum of initial conditions. That is to say, one region might have a significant overdensity, another region might have a slight underdensity or a significant underdensity. And you stack up all of these sound waves from all of these positions throughout the universe, And what you get when you average a bunch of these things together, or sum up a bunch of these things together, is you get something that looks like the cosmic microwave background that we observe, with the physics all being encoded in those sound waves. Now, we don't see these nice individual circles, but because all of the physics is still there in the sound waves that govern this pattern, we can look for the statistics of those sound waves and extract the content, the physical content of the way those waves propagated through the universe, and thus infer the properties of the early universe. There's one more bit of information that we rely heavily on to extract information about the early times. It's not just the density that we can observe, but it's also the polarization of the cosmic microwave background. This is an inevitable consequence of having this transition from an opaque plasma to a transparent gas. And this is due to the fact that Thomson scattering, which governs the interaction of the photons with the free electrons, naturally produces linear polarization in the presence of a quadrupolar anisotropy in incoming radiation. So this is what's shown in this animation here. So there's a free electron at the position where I stand. If there are hotter photons, more energetic photons coming from my left and right, as compared to up and down for me, that will tend to jiggle the electrons at my position preferentially up and down. And so photons that are scattered toward you will preferentially have their electric field aligned up and down, which means there is a net linear polarization that's produced due to quadrupolar anisotropy in the presence of Thomson scattering at the surface of less scattering. And so that I just walked you through dictates that there's linear polarization. There is no physics that gives you circular polarization with the cosmic microwave background. And so we can encode all of the polarization information of the cosmic microwave background just in terms of the Stokes Q and U parameters that denote the linear polarization of CMB photons, or photons in general, but CMB photons in particular. And those Stokes Q and U parameters define headless vectors on the sky. That is a spin-2 field across the whole sky. And so what we can do is denote the polarization in any direction with one of these headless vectors, just like a line segment without any particular associated direction up or down. You can always decompose such a spin-2 field across the sphere into curl-free E modes and divergence-free B modes. So these E and B modes are meant to make you think of electric field and magnetic field, and they're distinguished in particular by their parity properties. So if you look at a pattern of E modes in a mirror, you get back the same pattern. If you look at a pattern of B modes in the mirror, you get back the opposite side. And this is a physically very useful distinction to make, in part because while both density perturbations and primordial gravitational waves source E mode polarization in the CMB, density fluctuations do not source B mode polarization, but primordial gravitational waves do. And so searching for this primordial gravitational waves through the B mode polarization of the cosmic microwave background is one of the key goals of upcoming CMB surveys. All right, so all of the information content of the CMB, as I've described so far, is contained in the temperature fluctuations, temperature anisotropies, plus these polarization modes, the E mode polarization and B mode polarization. And then in addition to that, so you get a snapshot of all those things, which correspond roughly to the density and the motion of the plasma at early times, plus the imprints of structure that intervene between us and the surface of the scattering. Now, what we're interested in is not so much the distribution of the temperature and the polarization, but rather its statistical properties. That is to say, we don't necessarily care if there's a hot spot over there and a cold spot over here. What we do care about is the statistical information contained in those fluctuations. Now, due to the initial conditions from, we think, inflation, the initial spectrum of fluctuations is very, very nearly Gaussian, which means all of the statistical content is contained, or nearly all of the statistical content is contained in the 2-point correlation function. And we can analyze those 2-point statistics by computing the 2-point correlation function, calculating the harmonic transform, which gives us the angular power spectrum, which is shown here. On the top, you have the angular power spectrum of temperature fluctuations, and then E mode polarization, and then B mode polarization going in decreasing order of amplitude. And these bumps and wiggles that appear in all of these spectra come from that acoustic physics that I mentioned earlier This is effectively the Fourier transform of that sound wave that propagated out from the initial density perturbations. And it remains present in the maps despite the fact that we don't see a single perturbation, but we see a bunch of these stacked up. And so that statistical information is carried forward into the angular power spectrum. And by measuring these bumps and wiggles, we can infer the contents, evolution, and history of the universe. One thing I'll note is that these blue lines correspond to the B modes that are produced by inflationary gravitational waves or different amplitudes of the tensor spectrum. But an important part of our story will be that there's another contribution to the B modes, which come from gravitational lensing. I'll come back to that later on. And so up to now, our observations of the cosmic microwave background have basically focused on measuring these fluctuations and inferring these spectra from which we can analyze the contents, evolution, and history of the universe. Here is a nearly complete, up-to-date, or almost up-to-date snapshot of our observations of the temperature, E mode, and B mode power spectrum from CMB observations from a set of different observatories shown here. And what we can do is we can analyze these spectra and infer the contents of the universe from which we see that the universe is dominated by some form of dark energy consistent with the cosmological constant, with a large fraction of the matter being in some form of non-luminous, non-baryonic dark matter, with only about 5% of the energy budget of the universe being made up of ordinary stuff of everyday experience. Now, looking forward, there are several observatories, several surveys of the CMB that will be conducted in the coming years, which will drastically improve on the measurements that I just described. So notably here we have Simon's Observatory starting around, it's under construction, being deployed, CMB-S4, and potentially CMB-HD a little bit later. Those are all ground-based observatories that will have quite high angular resolution. There are future satellite missions that have been proposed, PICO and PIXI. The little stars here, by the way, just mean, roughly speaking, the ones that I'll mostly focus on. Those also happen to be the ones of which I'm a member, and then as John mentioned, I'm the Science Council co-chair for CMB-S4, so I'll pay particular attention to CMB-S4 as I go. All right, so that was the lightning review of CMB science. From here, I'm going to move on to one of the big new opportunities and potentially big new challenges that we'll have to face with upcoming CMB observations, and that has to do with the gravitational lensing of the cosmic microwave background. So gravitational lensing of the cosmic microwave background refers to the basic idea that the distribution of matter varies across the sky, and variations in the gravitational potential along our line of sight to the surface of last scattering causes CMB photons to be deflected on their path to us, and that leads to a distortion of our view of the cosmic microwave background last scattering surface. What it does to maps is shown in this simulation here. Here I'm showing you the unlensed E mode map on a 5° by 5° patch of sky, and then an unlensed B mode map for a simulation in which we've chosen there to be no primordial gravitational waves, and so the B modes vanish in this case. I'm going to lens these maps with lensing potential that looks like this, though it's the same size. I just showed a small version here. And after lensing, the most prominent effect that you can see is that the B mode polarization is no longer 0. And that's due to the fact that the deflection of the E mode polarization does not respect this parity separation that I discussed earlier. If you deflect around the E mode polarization, you naturally produce some E mode polarization. So the most prominent effect is that you get non-zero B modes. If you look closely, you can see that the pattern of E modes that you get is correlated with the E modes you started with. And it's also correlated with the lensing map. But if you look more carefully, as I flip back and forth between unlensed and lensed, you can also see the change to the E mode polarization on the left. Sorry. And what you can see is that various parts of the sky are magnified and demagnified. And that has to do with the fact that some regions of the sky are deflected outward or inward based on where the potential is origins. So roughly speaking, what I'm saying here is that lensing causes a change to the statistics that varies across the sky. So regions where there is more deflection, so for example, if a region of sky is magnified, you will change the statistics. You'll change the positions of the peaks, the peaks of the power spectrum as measured locally in that region of sky. And that change in statistics allows us to estimate, to reconstruct the lensing field itself. So we can look for that change in statistics and statistically infer the presence of the distortion that led to this change in statistics. Another way you can do it is to correlate the E modes and the B modes that were produced by lensing. I said the B mode map came from E modes, and so you can look for correlations between the observed E modes and B modes and reconstruct this lensing map. The Planck team has done this across the whole sky and made a map of CMB lensing, which has been observed at high significance, 40 sigma detection of the effects of CMB lensing across the sky. And this is great. This gives us a measurement of the integrated mass density throughout the whole universe that can be inferred statistically by looking at the changes to the local statistics of the cosmic microwave background and exoplanets. And this is wonderful. But it's both a blessing and a curse. CMB lensing allows us to be sensitive to the growth of cosmological structure because all of the stuff that intervenes between us and the surface of last scattering is responsible for that deflection. And so by measuring the effects of lensing, we get a handle on what is the stuff that intervenes between us, the distribution of matter between us and the surface of last scattering. And so even though the CMB really is this snapshot at 380,000 years after the onset of hot Big Bang evolution, it allows us to infer the distribution of stuff that intervenes all the way up until present day. And so we get a measurement of the 3D volume of structure and not just this 2D snapshot. On the other hand, lensing distorts our view of the last scattering surface, and that can affect our ability to infer the physics that results in that surface of last scattering. So in particular, if we're searching for the B-mode polarization that's produced by primordial gravitational waves, and there's all these lensing B modes that are produced, that becomes a source of confusion. And so lensing has this kind of dual role, where it helps us measure the structure, but it hurts us if we want to measure things that are most strongly imprinted on the surface of last scattering and not thereafter. Now, furthermore, I said there was a 40 sigma measurement of lensing with the Planck data. This is going to drastically improve with upcoming surveys, upcoming CMB surveys. And so what we do when we're analyzing a map of the CMB lensing is this map is also quite Gaussian, and so almost all of the information of the map is contained in the 2-point statistics. And so just like for the CMB temperature and polarization, we take the angular power spectrum of this map, and we can represent then how well we're measuring it and look at the features and how it changes with various changes to cosmological parameters. So the signal, that map gives us a signal that looks like this. And then these colored curves show us the noise with which we measure those power spectra. And so you want this noise to be small compared to the signal in order to make a high fidelity map of the lensing. What's shown in yellow is kind of an approximation of the Planck noise curve from lensing. And then going from yellow down to, let's just look at the bottom line here. This is what kind of the optimal analysis of the CMBS4 lensing map. And so you can see where we're only just getting signal to noise of 1 per mode at the peak of the lensing signal. With Planck, we will map at high fidelity all the way out to L of about 1,000 with CMBS4. So the effects of lensing, while they are measured at high significance now, will be precisely mapped with CMBS4 in the future. And so therefore we want to do all that we can to leverage this information to make the most of it. We will have a very, very high significance measurement of it, and we want to use that to do science. Now there's a few other features in this plot that get into the technical details a little bit. So you'll notice I've listed all of these red and purple lines correspond to particular lensing reconstructions with a CMBS4-like experiment. These TT and EB refer to specific types of estimators. So the standard analysis for constructing a lensing map like this is called a quadratic estimator, where you take products of pairs of CMB maps, and the 2 CMB maps you take are just denoted by the symbols here. So TT means I would take 2 copies of the temperature map and multiply them together with some filtering to produce this map. EB means I take the E mode polarization and multiply it by the B mode polarization to produce a map like this. MV just means minimum variance, so I'm taking the combination of all such pairs and giving me the lowest variance combination of all those things. The other thing to notice is the difference between the solid line and the dot dash line, which refers to iterative delensing in the case of the solid lines. And iterative delensing refers to a procedure by which you don't just take your first estimate, but you estimate the lensing, then you reverse its effects, you delens with your best estimate of the lensing map, and doing so removes some of the variance in the map that comes from lensing itself. So this is most obvious in the case of the EB estimator. So you can see that if there were no primordial gravitational waves and no noise, all of this has come from lensing. And you could say all of this is definitely from lensing. In the presence of noise, you don't have that luxury. So you get a combination of the lens B modes and the noise, but if you can reduce the amount of B modes that you see in your map, you get a better estimate of lensing. So by reversing this effect, you get closer to this, and you can then improve your estimate of lensing. And so this iterative procedure basically consistently improves your estimate of the lensing by removing the variance that's imprinted by the lensing. And it's not so obvious, but it works both for the TT and then for the EB. It's a little bit more obvious because you're reducing the payload power as you go. Okay, so the basic idea is measurements of CMB lensing will improve dramatically with upcoming observations, and we start to worry about what is the best way to extract all of the information. One more subtle thing that I'll note here is that across most of the spectrum, the EB estimator will be the best way that we can observe the CMB lensing. That is, it has the lowest noise. This purple solid line is the lowest across a wide range of angular scales. However, at very small angular scales, it's actually the TT that does better than the EB, because our measurements are more signal dominated, to higher L for T than for E. I'll come back to that point a little bit later. All right, so this is all great. So we'll measure CMB lensing with much higher precision with future data than we do presently. But you might ask, why do we care? What is the science that you get out of measuring the CMB lensing? After all, in a very standard lambda CDM scenario, if you know the parameters that go into your lambda CDM model, you predict exactly what the lensing spectrum is. So what information are you gaining by actually measuring the lensing spectrum? So the obvious answer is that we care about it because we don't know that lambda CDM, we in fact know that lambda CDM is not the complete answer. And so as soon as you start modifying your cosmology, you can start changing lensing, and you can change it in ways that don't show up explicitly in the measurements of temperature and polarization, but do show up in the lensing spectrum. So one example of this is given by neutrino mass. I won't spend a huge amount of time on this, but the basic idea is that we know from neutrino flavor oscillation experiments that neutrinos have non-zero mass, but we don't know the absolute mass scale. What we know is the mass squared splittings. We also don't know the ordering of the neutrino masses. In cosmology, we are sensitive to the sum of neutrino mass eigenstates, the sum of the masses of neutrino mass eigenstates. And in these two scenarios, the normal ordering and the inverted ordering, there are two definite predictions for the minimum mass of the sum of the masses of neutrinos. In the normal ordering case, that's about 60 millielectron volts. In the inverted ordering, it's a little over 100 millielectron volts. So these sums of masses set a clear target for our measurement of neutrino mass. We expect in the standard model that we have at least this much for neutrino mass, for the sum of neutrino masses. Now, cosmology is sensitive to neutrino mass because it's sensitive to the gravitational effects of any of the constituents of the universe. And the cosmic neutrino background, which is produced much in the same way as the cosmic microwave background, that is, the universe transitioned from being opaque to the transport of neutrinos in the early universe to being transparent to neutrinos after the universe dropped below about 1 mega electron volt. That led to a background of cosmic neutrinos that fills the universe. Those neutrinos still exist at a very high density, but because the neutrinos were born hot, that is, they act as hot dark matter, that is, sorry, let me back up one step and say they were relativistic at early times, but at least two species are non-relativistic today because the temperature of the cosmic neutrino background is below those masses implied by the mass squared splittings. What that means is the neutrinos make up a fraction of the non-relativistic matter density today, but those neutrinos don't cluster in the same way as cold dark matter. And that leads to a suppression of the matter clustering as compared to a universe that contains only massless neutrinos. And so this is showing the matter power spectrum in a universe with the minimal sum of masses of neutrinos compared to the matter power spectrum in a universe that has only massless neutrinos. And what you can see is a suppression of the clustering of matter on scales below the free streaming length of neutrinos. And so it's this effect that we want to look for in cosmology to extract information about neutrino mass. All right, this, I should also say, this suppression is quite small. We're talking about on the order of a few percent for the minimal mass of neutrinos. And so we want to very precisely measure the amplitude of matter clustering. There are many ways that we can measure the matter clustering in cosmology. I'm showing you a few examples here. Starting from the bottom in red, we have the count of galaxy clusters. So how many of the largest bound structures in the universe form the galaxy cluster. You can tell how what is the amplitude of the matter power spectrum. You can do the same thing with galaxies. So galaxies form at the peaks of overdensities in dark matter halos. And so by counting up the number of galaxies you have throughout your universe and how those things cluster together, you can measure the distribution of matter throughout the universe. And you can also do this with CMB lensing. And what this plot is showing is where are you sensitive to the matter power spectrum as a function of scale on the horizontal axis, larger scales to the left, smaller scales to the right, and as a function of redshift. Now with CMB lensing, what you get is a measurement of the clustering of matter that's sensitive to a wide range of redshifts because CMB lensing measures the integrated line of sight density. All of the stuff that intervenes between us and the surface of left scattering can deflect CMB photons. You're dominated by the signal that comes from linear scales, large angular scales. This dot dash line here denotes the separation between what we can consider linear fluctuations and nonlinear fluctuations on the right. Nonlinear fluctuations refer to those where the effects of gravity have become nonlinear, and nonlinear growth has started to dominate, so you can't rely on linear order perturbation theory to make predictions over this region. So CMB lensing is valuable because it gives us a bunch of signal to noise to the left of this curve, where we can make definite predictions from standard cosmology. And for the purpose of neutrino mass, we're interested in things that are to the right of this purple line, where you get this suppression in matter clustering, and then to the left of this red dot dash line, because we can make predictions reliably in linear theory. So CMB lensing gives us a bunch of sensitivity in that. And here's just a different view of this, saying that if you take the power spectrum of the CMB lensing, you can see the effect of the suppression due to neutrino mass. So this is showing the change to the lensing power spectrum for the minimal sum of neutrino masses compared to a universe with only massless neutrinos. You get this big suppression, and then the error bars shown here are what's forecast for CMBS4. And then I plotted this for both linear theory and nonlinear theory. And so even if you don't trust your predictions up in this region where linear and nonlinear disagree, you can make very good measurements of the suppression that comes from CMB lensing, and therefore get a good measurement of neutrino mass that, depending on some other things that I won't get into, are guaranteed to make at least a low significance measurement of the minimal mass of neutrinos.
Joel, I don't understand the sign of the effect. If neutrinos have mass, then there's less matter cluster.
That's right.
Because they screen a smaller distance.
Yeah, good.
So why would there be more matter cluster?
Yeah, that's a great question. Ultimately, a lot of these questions come down to what you hold fixed when you ask the question. And so in what I've held fixed here is kind of listed very quickly here.
Yeah.
But what we hold fixed is tied to what we observe. And one thing we observe is the expansion history in the recent universe, which is dominated by dark energy, but then also the matter density of the universe, the non-relativistic matter density. And because the neutrinos, despite what the perturbations do, the neutrinos contribute to the non-relativistic matter density of the universe, they contribute to the expansion history in the same way as the dark matter over the relatively recent cosmic history. And what that means is, in your analysis, it's most natural to hold omega matter fixed, but omega matter includes contributions both from dark matter and from neutrinos. And in that case, part of that dark matter, or part of the matter, just doesn't cluster, and the neutrinos just don't cluster. You can actually trace this, well, I didn't include the equation. You can trace this back to that being one of the contributions to this suppression. There's another contribution which is more subtle, which is that not only do they not cluster, but they actually reduce the potential well into which the dark matter falls. and that adds to the amount by which there is a suppression. So yeah, there are those two subtle effects, but roughly speaking, it comes down to what you hold fixed. If we hold fixed the total matter density, then you have a component that doesn't cluster, and the potential wells are smaller than they would have been in the absence of neutrinos.
Okay, I'll think about it.
Okay. I should ask if there are any other questions. I'm more than happy to take them as well. Okay. Good, so we can make this measurement of the clustering of matter, which allows us to infer things like the neutrino mass. Neutrino mass is not the only type of physics that we're interested in, but it's one example which is guaranteed to be there in standard model. It's challenging to measure. We're talking about a few percent suppression. And so this provides a good benchmark for the type of precision that you can get with measurements that come out of CMB lensing. I will just say one more word that neutrino mass measurements are more interesting than they might sound. Even if you're a cosmologist who doesn't really care about the hierarchy, whether you're normal ordered or inverted ordered, there are reasons to care about this measurement. So one set of things is particle physics motivation. So specifically, there are laboratory-based measurements of the effects of neutrino mass that probe different aspects of neutrino mass. And by having a measurement of the absolute mass scale of neutrinos, cosmology sets targets for things like neutrinoless double beta decay, endpoint measurements from beta decaying species, and provides a very complementary probe as compared to laboratory physics. Okay, but again, even if you don't care about neutrinos per se, the measurement of neutrino mass in cosmology provides a very robust, very stringent test of our cosmological models from end to end. So neutrinos, the existence of the cosmic neutrino background, relies on physics that operated at 1 second after the onset of the hot Big Bang evolution, all the way up through cosmic structure formation, up until redshift 0. And if we measure something that deviates from this minimal mass or from something that's commensurate with our observations from particle physics, that's a signal that something else could be going wrong in our cosmological model. And it may not point to exactly what goes wrong, but it does, if it succeeds, if it matches our observations, we actually get a very, very stringent test end to end. It's also worth saying it's not only neutrinos that can result in this sort of physics. If you have new species which are light but have non-zero mass, they result in very similar physics, not identical physics because their temperature need not be the same. And so you can look for the similar effects, which allows you to probe new light species, including things like the gravitino, which are very strongly constrained by this type of analysis. And then finally, even if you say, okay, all that stuff also sounds esoteric, measurements of the neutrino mass or the suppression of matter clustering due to neutrino mass are also very strong probes of things like astrophysical processes. So in particular, if you have different probes of this matter suppression, they're differently affected by different physics, including neutrino mass, but also including things like baryonic feedback, supernova feedback, things like that that can affect the clustering of matter on small scales. And by pinning down the neutrino mass with a measurement of CMB lensing, where the physics is linear, you can do a better job at backing out those baryonic effects, which are more relevant on small scales if you compare it to things like cluster counts and galaxy clustering. Okay, but again, it's not just neutrino physics, it's not just this measurement. What we care about in general from CMB lensing is that we get a measurement of the matter density integrated throughout all of cosmic history across a wide range of scales. And so things like warm dark matter, axion dark matter self-interactions, all of these things can affect clustering. And CMB lensing in principle provides useful information about all of those things. And so hopefully that motivates to you that we want to do as well as we can at measuring the effects of CMB lensing. So we want to obtain the most robust and most precise measurement of CMB lensing that we can muster from our data. Okay, so let me motivate that we might want to think differently about the way we reconstruct lensing by going back to what is the effect of lensing, not on the maps, but on the CMB power spectrum. So what I'm showing here is the power spectrum of CMB temperature for the unlensed spectrum, shown in orange, the lensed spectrum shown in blue, and then the delensed spectrum shown in green. I'll come back to that in just a second. But what you can see, the difference between the blue and the orange, which is easier to see in the bottom panel, where I'm showing not just the, I want to show the difference compared to the unlensed spectrum. On large angular scales, to the left on this plot, you see this wiggle feature. This wiggle comes from the fact that one effect of CMB lensing is to smooth out acoustic peaks. So any feature that has a particular angular scale will be spread out by lensing because various regions of the sky are magnified or demagnified. So if you have a map that have all exactly 1 degree circles, CMB lensing would make some of those 1 degree circles a little bit bigger, and would make some of those 1 degree circles a little bit smaller. So what you started out as a delta function would be spread in angular scale. And the same thing is true for the acoustic peaks of the CMB. So what started out as prominent features at particular angular scales, as shown in L, gets spread out a little bit, and that results in these wiggle features in a difference. So peaks are suppressed, troughs are filled in. And that's the wiggle that you see on large angular scales. On small angular scales, there's a slightly different set of physics that's going on. What you can see is that lensing seems to be adding power. Strictly speaking, lensing is not adding power, it's only transferring power from large scales to small scales. But you can see that at small angular scales, the power spectrum in the lensed case exceeds that of the unlensed case. That's kind of hard to see down here, but let me show you a different view of it. If we zoom in on this damping tail regime. By the way, this is called the damping tail because this is actually the power spectrum of the unlensed temperature is exponentially suppressed due to diffusion damping of the photons around the time of recombination. So the unlensed signal is dropping exponentially, but the lens signal hits this plateau. And that plateau region, which you can see zoomed in here on the right, allows for the lensed power spectrum to be significantly larger than the unlensed spectrum. In other words, on these angular scales, it's the effects of lensing that dominate our observations of the CMB temperature. And what that means is when you observe these small scales, you're directly observing the effects of lensing. And furthermore, because we know how lensing works, we expect that while this is the power spectrum, this doesn't actually contain the whole story because these modes are non-Gaussian. The way that lensing works on small scales, if you started with a pure gradient in temperature and put a bunch of small scale lenses down, you would get a bunch of little temperature dipoles because the deflection of the photons would bring some of the power from the high temperature side to the low temperature side and vice versa. So you get a bunch of little temperature dipoles. And so the power is dominated by the lensing CMB secondaries in this regime, and the fluctuations are non-Gaussian in this regime. And so that motivates the fact that maybe we should think about a different estimator that's optimized for this regime as opposed to the current estimators which are dominant for this peak spread regime. Now let me just make one more point here, which is that even if you do your best estimate of the map-based reconstruction of the lensing, and you remove all the lensing modes that you can measure well, that is represented by this green line, the D-lens line. That's what it means to D-lens. You make the best possible estimate you can of the lensing, you remove its effects. That gives you the green power spectrum. And what you can see is that even after D-lensing, you're still lensing dominated on these small scales. This dot dash line shows the rough noise level, the noise power from a CMBS4-like experiment. And so when you are in the signal-dominated regime, that is when you're above this green dot dash line, you're still lensing dominated. And so that motivated Victor, Renee, and myself, and Alex Van Engelen to think about, are there ways to better measure the lensing in this small-scale regime? Okay, and so this very nice plot put together by Victor shows this non-Gaussianity that I was referring to. So the small-scale power is not the same everywhere in the sky, because the small-scale power in this lensing-dominated regime comes from the fact that you have large gradients, large temperature gradients on large scales that are being lensed by the small-scale lenses. And because the temperature gradient varies from patch to patch on the sky, you can see that the small-scale power also varies from patch to patch on the sky. So what's being shown is this is the amplitude of the lensing temperature gradient power on the horizontal axis, patch by patch. And on the vertical axis is the small-scale power, small-scale temperature power. And so if you sort things by where the gradient is large and where the gradient is small, you see a trend line that you get more power where the gradient is large and less small-scale power where the gradient is small. And this motivates thinking about, can we use this trend to extract information about the small-scale lensing? And in fact, the answer is yes, you can. And so this is a different view of the same physics. So on the top row, we're showing here just the unlensed temperature and the lens temperature. And by eye, it's really hard to tell the difference between these two things. You can also take the large-scale gradient power of the unlensed and the lens maps. And these things are almost identical because the effect of lensing on large scales is relatively small. It smears the peaks, but it doesn't really change the features all that much. And then you can look at the small-scale gradient power from the unlensed and the lens map. And here you see a huge difference. And this huge difference basically just comes back to this idea that the unlensed power is way down here and the lens power is way up here. And you can see that in the map. You have much more small-scale gradient power in the lens case than the unlensed case. And then the next thing you can notice is that you can see that this map is correlated with this map. Okay? So where you have large features like here, you can see there's a large feature here, and here, and here. And so these things are correlated. And you can think about, can I use the fact that these things are correlated to extract information about the small-scale power? And indeed you can. So if you take these maps and you filter them on different angular scales, what you can see is that they correlate very well across different angular scales. And this now allows you to construct an estimator where you make maps of the large scale gradient power, you make maps of the small scale gradient power, and you cross-correlate those maps. And you can use that to estimate the small scale lensing power. And so this is what we did, again, with Victor, Renee, and Alex Van Engelen. We constructed this scale estimator, small correlated against large estimator for lensing, which does the kind of thing I said here. And what we showed is that you can actually, at CMB-S4-like noise levels, surpass what you might expect from standard techniques of lensing reconstruction with these feature data. All right, good. So we care about measuring the best lensing map that we can, and the best lensing statistics that we can, and this scale estimator provides a way that we can do that to get as much information as we can about the structure that intervenes between us and the surface light scattering. But we also care about the fact that lensing distorts our view of the CMB, and so we also want to be able to remove the effects of lensing. So the next part of this, I'll talk about how lensing acts as a hindrance to our measurements of various cosmological parameters and why we might want to remove it. All right, so this is a plot that's exaggerating that peak smoothing that I was showing you earlier. So this A lens parameter just denotes the amplitude of lensing. It's a fictitious cosmological parameter that you can just use to scale the effects of lensing. And as you go from unlensed, when AL is 0, to a situation where you have 8 times as much lensing as we have in our real universe, you can see that you smooth out these peaks. So as you increase lensing, you reduce the peaks and you fill in the troughs as you smooth out these acoustic peaks. Now, if we can measure the lensing, measure a map of the lensing, and reverse its effects, we can undo this peak smoothing. And so delensing allows us a way to sharpen the peaks. And so that's being shown here for the TE power spectrum for a few different experiments. The purple is roughly like Simon's Observatory, the yellow is roughly like CMB-S4. And you can see that after delensing, you recover these sharper peaks that you had prior to the effects of lensing. Now, why does that matter? It matters because sharper peaks are easier to measure in the data. That is, if you have a sharp feature, it's easier to localize that sharp feature than it is to localize the broad feature. And so that's being shown in this plot. So the left panel shows the error on the peak position in L space for the unlensed data and then delensed for these different experiments. And you can see that, so in this lower is, I'm sorry, I should say, it's compared to what you would get for lensed data. So in this plot, lower is better because a smaller error bar on the peak position allows you to localize it better. And so delensing allows you to reduce the error bars with which you can measure the peak position. On the right, you're seeing the same thing, but for peak heights. And so peak heights are also better measured when you delens. Okay, so great. So you can better measure features of the power spectrum after you delens. And as I said before, the peak positions, the features that show up in the angular power spectrum are associated with the physics of the sound waves propagating through the plasma. And that allows us to better measure cosmological parameters. So just to give you one example of this, this is something we reported in this paper that came out just last week with my undergraduate student, second-year undergraduate student, Josh Hage. And we were looking at models that address the Hubble tension can be better constrained with CMB lensing. So let me just walk you through this very rapidly. So the way that we infer the Hubble constant from the CMB is that we measure the angular scale of the sound horizon, which has to do with the spacing of the acoustic peaks in the CMB. There's a physical size associated with the sound horizon at the surface of last scattering that just has to do with the amount of expansion prior to recombination and the sound speed in the plasma prior to recombination. And then by measuring the angular size and knowing the physical size, we can infer the amount of integrated expansion that has occurred between the surface of last scattering and today, and that allows us to measure the Hubble constant. What that does, so if you change the Hubble constant, what it does to your CMB spectra is shown here. The fact that these wiggles show up implies that changing H0 leads to a phase shift. So you're shifting the position of the peaks and the troughs. And as I just said, delensing allows us to better localize the peaks, which indicates that by delensing, you might be able to better constrain the types of parameters that affect peak positions. And so what we did in this paper is just to walk through some of the proposed solutions to the Hubble tension. And sorry, I should say, this is the way we infer it from the CMB. You can also make direct measurements of the Hubble constant from things like the cosmic distance ladder. Those numbers disagree by a small amount. I'm not a big proponent of the Hubble tension, so I'll leave it there. Right, so there have been a number of models proposed to address the Hubble tension by altering the physics in the early universe, which shifts the size of the sound horizon and correspondingly shifts the positions of the acoustic peaks in the CMB, and therefore you infer a different Hubble constant. What we showed in this paper is that for various of these solutions, you're able to better constrain the parameters that dictate those models and ease the Hubble tension. So one such model is varying fundamental constants. If things like the electron mass and the fine structure constant were different at the time of recombination than they are today, then recombination physics is different than what we would infer from laboratory-based experiments of atomic physics today, and that shifts your inference of the Hubble constant. And what we showed is that if you delens your spectra, you can actually much better constrain the variation in the electron mass and the fine structure constant, and then correspondingly the Hubble constant from CMB data. There's this notion of early dark energy, that there was maybe an additional component prior to recombination, which changed the amount of expansion prior to recombination, which was dark energy light. That's denoted by the fraction of energy in dark energy, the transition redshift, where did it transition from being dark energy light to an oscillating scalar field, and then some initial misalignment angle. And then all of those things are correlated with the degenerate with the Hubble constant. And delensing, again, allows you to improve the constraints. Sorry, I should have said on these plots, lensed is blue, delensed is yellow, and then the unlensed is the pink dash. Lower is better because smaller error bars are better, and so you can see going from the lens data where you do nothing to delensing improves these error bars significantly in a non-trivial way. The horizontal axes and all of these things are the noise level, and the cost of the experiment scales as the square of this or the inverse square of this axis. So reducing by a factor of 2 in noise requires an increasing factor of 4 in the cost. So while the improvements look modest, for example, on this plot, you can notice that just throwing more detectors at it doesn't improve these parameters very much, but delensing actually does a significant improvement without requiring image changes. All right, and then one more example, interacting dark radiation. If you put some new species that self-interacts, so it's not like neutrinos where they free stream, but they self-interact and act like a fluid, that can also ease the Hubble tension. And again, delensing improves constraints on interacting dark radiation models. Yeah, so again, just to give a plug to my undergrad student, Josh Ainge, he's a really excellent second-year student, did a wonderful job on this. Okay, I think I'm out of time. I think I'm going to skip this machine learning stuff. I'm more than happy to answer questions about this. The very brief one-sentence summary here is that we're moving to a regime where we are trying to extract nonlinear, non-Gaussian statistics from very high precision data. Machine learning is well suited to address that problem, and we showed ways that you can do that and simultaneously reconstruct various sources of CMB secondaries, and also recover primordial nodes. So with that, I will wrap up and just say that There's a lot to look forward to with upcoming CMB surveys for constraining particle physics, cosmology, and astrophysics. And there are new challenges associated with making the most of those observations. And we are in the process of building new tools to best tackle those challenges to make the most of those observations. So I'll stop there and take questions. Thanks very much.
So I'm going to ask if students in the room specifically have any questions for Joel, either undergraduate or graduate. Chris, you're a student at heart.
Eternal student. So, can we go back to the very beginning where you showed the signal versus measures versus L? Yes.
This one?
So there's this broad shoulder in the mode signal between 20 and 100.
Oh, this?
Yes.
Mhm.
What is that due to?
This is due to, so this, all of the things to the right of this dip are due to the same acoustic physics
Yes.
that show up here.
But my impression is that it's a little bit less peaked than the temperature.
Yes, that's right. You'll also notice it's misaligned, right? So this shows up not at the same position as this peak. This actually corresponds roughly to a drop.
Well, I'm sorry, the emo is covering many decades, isn't it? So I'm being mainly followed by the logarithmic scale.
Oh, you're asking, so why does it go up? Whereas,
Well, I guess I wondered why there's that shoulder. Yeah.
yeah, here?
Yes, exactly.
Yeah, so this just has to do with the fact that that all of the modes to the left of this here came from fluctuation modes that are actually outside the horizon at recombination. And so you get an enhancement in the polarization if the plasma is able to move prior to recombination, but none of this did. None of the modes over here had any opportunity to move. And so you're dominated over here by just the contribution, not from the Doppler effect to the polarization, but instead just by the intensity variations. In other words, the quadrupole for these modes is smaller than the quadrupole for these modes because they were super horizon at recombination, whereas these modes were sub-horizon.
If you plug in correlation function space, does it go to exactly zero? I've never been in the past by my Finland on our and I think if you do the Fourier transform of this plot in real space, the E might actually go to exactly zero beyond 1 over that angle.
Right, and so, yeah, and then, right, in the absence of this bump, which you're not asking about, in the absence of this bump, that fact in Fourier space is reflected by the fact that this goes all the way down here. Yeah, with like a lot long. And then this bump, just to fill in the detail of what I'm saying, this bump comes from different physics. This bump comes from reionization. So at much later times, there are free electrons due to the fact that the first galaxies and first stars reionize the universe at low redshift, but the same scattering of, the same physics of Thomson scattering resulted in this reionization bump. So you can't see the whole recombination physics because it's hidden in that bump.
That's what the primary thing that lets you measure tau accurate.
That's exactly right. So this is an important bump for measuring the optical depth to reionization. It's the same physics actually on the B modes. If we were lucky enough to measure these, then that provides an independent measurement of, I shouldn't say independent, but provides another measurement of tau.
Karen?
What about the sound horizon free measurements of H0 from CMB lensing? Will they improve with high resolution data like SO and S4? Or is the fact that you've measured that peak, you showed the nice sensitivity, right?
Yeah, those will improve dramatically. Dramatically. We are not yet signal dominated across this whole peak. And so, your question relates to, roughly speaking, how well can we localize this peak? And the difference between a noise curve, say here, And here is not very significant in localizing this peak. But because we're just scraping the surface, you actually can significantly improve the localization of this peak. But there would not be a big difference in going from SO to S4 in that measurement. So going from Planck to SO, big improvement, SO to S4, not so much.
So relatively modest improvements in the sound horizon-based stage notes, but maybe a significant improvement in this stage note.
Yes, that's a good point also. So just to maybe drive that point home, whoops, sorry, correction. Yeah, so the question for how well we measure the sound horizon associated with how well can we localize all of these peaks, and because we already have, we're already cosmic variance limited up to L of 1500, you're not going to do much better on the sound horizon for measuring these peaks in future data, except for the delensing thing that I said. So delensing actually does improve this measurement a little bit because you can sharpen these peaks, but it's not a drastic improvement in the standard model if you're just trying to extract the sound horizon, because you're already signal dominated across so many of these points.
And I think even these kinds of plots in the correlation space, these plots are very boring. They just have a little pink at the horizon and they don't oscillate at all. It's just the Fourier transform that gives you random peaks.
That's right. Yeah,
But you are measuring for it.
Well, right, well, people used to call these only correlation functions. And and for theory, it doesn't really matter. It's for experiments in Fourier space, the modes, the error bars tend to be more uncorrelated. So it's easier for you to visually link the error bars in Fourier space.
Okay.
Whereas in real space, they are highly correlated. It's harder to plot error bars.
that's right. That's right. Yeah, to put it another way, you could ask CAM to produce this plot, or the correlation function version of this plot just fine, and compare it to data. But the problem is exactly the error bars. The error bars are much easier to plot in this space. Just one more note about delensing. You could actually see the effect of delensing in terms of the peak sharpening, or you can see it more easily in terms of the correlation function. You actually get a sharper little wiggle in the correlation function by delensing in a way that's totally analogous to BAO reconstruction for folks who are familiar with that.
Do we have any questions from our online viewers? Feel free to either raise your hand virtually or just shout something out. Okay. Well, there will be plenty of opportunity to chat with Joel. He's around much of the rest of the week, a lot of open spots in his schedule. Feel free to come by his office. This was his office on the 14th floor. For now, let's just thank Joel again for a great seminar.
Thanks very much.